Awesome. Thank you, everybody, for sharing your details on comment. We see that we have people from everywhere around the world joining us here. Hello from folks from India, Portland. We see people from Seattle over here and Sunnyvale, Santa Clara, SF as well, Vancouver. Hi, everybody. Glad that you could join us today. So for first, we have all of our agenda on DevFest West Coast. For the first talk, I have the honor to invite one of my friends, Hannes Hapke. He's a senior machine learning engineer at SAP. He's also a fellow Google developer expert on machine learning. He also recently wrote an amazing book on building machine learning pipelines, which is now available for sale as well from O'Reilly. So feel free to take a book, go order on Amazon. And yeah, for a short summary, I'm assuming for that book, here's Hannes. Go on.
Vikram, thank you very much for the very kind introduction, and also thank you for having me today to talk about TensorFlow Extended. And it's great to be part of that amazing DevFest West Coast 2020. Yeah, let's jump right into the presentation. So what I want to talk about in the next 30 minutes is how we can take our machine learning models we have trained in our experiments, and how do we turn them into pipelines so we can use them consistently in products. Just real quick, as Vikram mentioned, I work at SAP. I'm one of those GDEs, as you can see in that photo here. And together with Catherine Nelson from SAP, we both co-authored the O'Reilly publication, Building Machine Learning Pipelines. And today's talk is a very, very, very brief summary, and some slides might be abbreviated, and we might rush through some content here. So if you want the complete deep dive, I highly recommend that publication. Before we get into all the TensorFlow Extended details, let's quickly talk about machine learning engineering. When we normally talk about machine learning in presentations, we talk about algorithms, we talk about new architectures. This is basically the orange, or the orange box here. So we talk about machine learning frameworks, PyTorch versus TensorFlow, et cetera, et cetera. But when we want to take those trained models into production, the ecosystem looks much bigger. So all of a sudden we have to take a look at how do we keep updating our models, how do we analyze the models, how do we serve them, things like this. And those topics is what we understand these days with the term machine learning engineering. So when I describe my job, I often say, like, it's sort of like the machine learning plumber. You take the data, you turn it into a model, you help with the training, and then I help with deploying those models and capturing the data from those deployments. But I'm not focusing on the actual ML code. That's what, in my opinion, data scientists do and what they're the experts in. But then when we take a look at, like, why do we need machine learning engineering? There's often the conception in the machine learning field that, hey, I train my models in my notebooks. Well, there's a couple things happening here. Yes, you get a trained model out, but there's no focus on reproducibility. There's no focus on traceability, which will become more and more important in the coming years. And we want to reduce the burden for data scientists. That's what I think the purpose for machine learning engineers is. We want to make it as easy as possible to update models, because if we, or data scientists, release models, we can't spend 2 hours each week for each model to update that and keep it up to date. That needs to happen automatically. And what I want to show in the next 30, 25 minutes is basically how can you do this with TensorFlow Extended. All right, so let's quickly talk about what happens to trained models in most situations. Well, sadly, they usually don't get deployed. Let's face it, because the whole ecosystem of machine learning engineering has been too cumbersome and complicated in the past. And a lot of data scientists have given up on bringing out their amazing work into a real life scenario. There is always a funnel. So let's say you have 1,000 experiments, maybe you tune 100 of those models and maybe 10 of them get deployed. But we might miss out wonderful opportunities to contribute back to society with machine learning and help with like applications if the deployment or like the operation of those machine learning life cycles is too cumbersome. There are some other aspects. Some models do get deployed, but then all of a sudden we have a whole different set of problems. Those models experience data drift. The schema might change. So we train with one set of data, and then 3 months later, maybe the database schema changes, and all of a sudden our training data downstream changes as well. We see training serving skews. There's like complicated pre-processing steps. Often they get updated without updating the model. The whole retraining is really complicated. When I speak with other data scientists, I hear stories of like, yeah, we don't update models because it's just simply too expensive and it takes too much time. And then we have like the whole ecosystem of like deploying machine learning models when it comes to like, ooh, how can I reduce the latency of my predictions and things like this. So this is what we describe it as the machine learning lifecycle. So basically, if you would draw it out in a very generic life cycle, so it always starts with the ingestion of the data. We validate the data. We pre-process or do some feature engineering there. We train a model. In some situations, also we tune our models. Then there's a very critical step, which I think often gets left out when we talk about machine learning life cycles. Is like before we deploy the model and after we train it, the model needs to be seriously analyzed and also validated. And then once the model is deployed, we really need to capture the feedback about the model, because that's our lifeline, and we can also use the feedback to generate more data. So that's why it's an endless cycle, as we'll see it. And as you can see, and as you can imagine, those systems are highly entangled. So meaning if you change some hyperparameters during your training, your model analysis and your model validation will look very different. You might have to validate it with different thresholds, and your serving might look different. So if you change one parameter, it has a whole downstream effect. So doing this manually will take a tremendous amount of time, and that's why the focus should be on automating those machine learning life cycles. And this is where TFX, or what we call TensorFlow Extended, is here to help. Basically, TensorFlow Extended provides you all the tools to automate your machine learning lifecycle. So if we take a look at this, this is basically the individual components. So we have like components in our machine learning pipeline. And here we start with like the data ingestion. We do some, again, data validation, pre-processing. Sometimes people do the data validation after the pre-processing as well. There are good reasons for that. But for simplicity, I've left it out here in that overview. We train our models, we validate them, and then we deploy them. And this all runs in the TensorFlow ecosystem. And then we can express those components and orchestrate those pipelines in various systems. And I'll talk about this in a couple of seconds here. But also, if you look at those components which TensorFlow Extended is providing, so basically for each step you see in those blue boxes, you have the white boxes, which are the individual components you can use from the TensorFlow ecosystem to build your machine learning pipelines. And then you have the orange boxes, which are the standalone libraries from the TensorFlow ecosystem, which you can use for your pipelines. And some of those components are framework agnostic. That's so if you have a PyTorch model, you can also use that with those components. Yeah. As I said earlier, once you design your pipeline, you can orchestrate that pipeline and you can run it in various ways. You basically have 4 different ways of running your pipelines. The first one, you see the Jupyter Hub notebooks there. That's technically not a pipeline, but in the TFX ecosystem, it's called the interactive context. Basically, you can run the individual components and you can debug those components. But some people use that in a notebook just to string a pipeline together. And if it works, they export it towards Apache Beam, Airflow, and Kubeflow. There will be a talk right after mine where you get a wonderful deep dive into Kubeflow. So I highly recommend staying on, watch the talk by Carl, and you will find out all the details about Kubeflow. But what I want to stress here, if you don't have Kubeflow set up, or maybe you work in a company or in a project where you already have Apache Airflow, you can also orchestrate your machine learning pipelines with Apache Airflow. All right, let's take a quick look how we can run TFX in action. A couple months ago, my colleagues and I at Concur Labs, we wrote this blog post at the Tensorflow blog of how we use BERT models in connection with TensorFlow extended pipelines. And the reason for implementing that as a TFX pipeline was A, we didn't want to update our model frequently, and B, we wanted to take advantage of TensorFlow Transform. In the interest of the time, I will not get into all the TensorFlow Transform details, but there are 2 blog posts with all the details. If you're interested in how we use it and why we use TensorFlow Transform for our BERT models, I highly recommend that blog post, as you can see here on that slide. But let me walk you through how we set up the pipelines. So again, first, any pipeline starts with the ingestion of the data. So here we have, we define our input data pipeline, and TensorFlow Extended has wonderful functionalities. One of the cool functionalities is you can ingest the data from a folder or from some cloud bucket. It could be GCP, S3, anything what Minio supports. And then you can split those data according to a ratio you set. It doesn't need to be a double split. So you can say, you can also have like an extra test set. It's totally up to you. It's highly configurable. But this split will be then considered in the pipeline for your training and for your validation and potentially your testing. And then once you have all the inputs and outputs configured, you can ingest the data. And for that purpose, TensorFlow Extended provides you numerous components. So in this case, we're loading TF record files we already pre-processed. This is a very generic import here. The reason is also we use a public data set that was already available as TF records. There are components out there for BigQuery connections. We internally wrote like components for HANA connections. So if you're like an SAP customer, you can easily connect. There's like numerous ways of ingesting the data. The wonderful thing I really want to stress here is under the hood, and you don't have to touch it. You actually don't see it. Under the hood, it is executing always everything on Apache Beam. So if you have like millions of files, Apache Beam will take care of the distribution of the data ingestion in that case. Once the data is ingested, we can do 2 amazing things. Number one is we can generate statistics of your data set. And here I want to stress, this is basically the one-liner is all you need to do. You basically point the statistics generator to your example data sets you just ingested, and then it will generate the statistics. And I'll show you an example here in a second. Once the statistics have been generated, you can also generate a schema. And I think a schema is often overlooked when we talk about machine learning pipelines or data pipelines. This will give you information of like, what are the columns? What are the features? Are the features dense? Are they sparse? What is basically, if you have categorical features, what are the labels? And the wonderful thing in TensorFlow Extended is those information will be stored in a metadata store, and you can later compare against previous runs. So for example, if we train a machine learning model today and we ingest new data, and let's say the data has updated or the schema has changed in the past, the pipeline would highlight us and say, hello, wait a second, there's a new column, or maybe there's a new label coming up in a categorical field. We can set thresholds where we can say, if data drifts in a certain direction, stop the entire pipeline and do not produce anything, but alert the data scientist. So here's an example of a visualization of the data we just generated. Also, and you will see this later on in the Kubeflow example from Carl, you can drill into the individual components, and some of those components have visualizations. So while the pipeline is running and continuously retraining your model from time to time, you get those amazing visualizations where you can drill into each feature, you can see the distributions, you can even compare the distribution and the data sets. There's a lot you can do with TensorFlow data validation. So once we have data not just ingested, but also generated the schema, and we have the statistics generated, then we can start diving into the feature engineering. And we can do this here with TensorFlow Transform. This needs its own talk to talk about TensorFlow Transform, so I just leave it with that. I just would say that you can express your data processing, pre-processing steps as TensorFlow ops, and because you do that as TensorFlow ops, you can build a graph out of this. And later on, when I show you how we export the model, you can attach the pre-processing graph together with the model graph from your trained model and export one artifact. This is a wonderful way to avoid a training serving skew when we serve machine learning models, and to always make sure that the pre-processing step is matching your latest machine learning model. So we just defined those TensorFlow ops. TensorFlow, the ecosystem, provides numerous wonderful manipulations. So if you're in the computer vision field, you can look into image manipulations from TF Images, or if you work with NLP problems, there's TF Text, where you get very powerful tokenizers for modern transformers, or like you need simple string transformations, you can always express them through TensorFlow ops these days. And if not, then under certain circumstances, you can also use TF functions to express your operations here. Once you have defined this, you save it in a module file, and in our case, we call this transform.py. And then we pass that to the transform component, where the component itself will look for the pre-processing fn function. That's basically the hook. And then it will apply those pre-processing steps to the ingested data. Once the data is transformed, we can start training our model. This is a way which was recently introduced in TFX, where we can use a generic trainer, which allows us to use Keras models. If you look at previous documentation, it always introduces, or we always had to use the TF estimator architecture. This is not the case anymore. I want to stress this. You do not have to train an estimator at this point anymore. But the wonderful thing is, because you have the pre-processing steps performed, we know the schema after the pre-processing, so you can easily load your machine learning models. That's basically, or your data, not the models, we're training them here. We can apply distribution strategies if we need to. Currently, TensorFlow Transform supports the mirrored strategy, because we can spin up individual external clusters to support more than the GPUs we have on hand, but that's at least, or that's so far a really good way of like distributing training capabilities. We load our models as usual. Like you define your models as through the functional API or through the sequential API. As long as it's a Keras or a TensorFlow model, that's totally fine. What I like to do is I prefer to pass in the transform output information, because then we can dynamically create the inputs to the model based on the previous step. The training and the serving, the training and the saving is exactly as we know this from previous TensorFlow or Keras models. We call fit, and then once we're done with the training, we save the model for future evaluations. And again, all those steps, we export them to a module file. In this case, we call this trainer.py. And then we pass this information to the component and say all the training information will be in that file. All right. We can also do the model analysis. the analysis steps are fairly lengthy. I really abbreviated this here. I highly recommend, if you're interested in like how to configure this in detail, take a look at the documentation from TFX or our publication. There's a lot. This is a really, really powerful component, because what you can do here is you can say, after the model was trained, evaluate the model with certain metrics. And the metrics are not just accuracy. This could be like an F1 score. It could be a precision recall. It could be whatever you want to define. And then you can take a look at specific slicing specs. So normally when you train a machine learning model and you run your validation set after every epoch, you would run it against the entire data set. And then you see like maybe an accuracy number or some loss, or maybe even an F1 score for this entire data set. But let's say you train a machine learning model and your data is like 80% from one country and 20% from another country, but you're trying to predict, like, let's say, restaurant reviews. You want to make sure that the model performance for country A is similar to the model performance for country B. But you can never see this from the model validation during the training. So this is where the model analysis becomes extremely powerful, because you can slice by countries and then make sure that the accuracy or the F1 score, whatever metric they use, is similar by country. And then if maybe there's an outlier, you can investigate further or stop the deployment. This is extremely powerful. So really quick, as I said, you define your specs, you define your metrics, and then you can either slice against the entire data set, which would be very similar to your normal validation during the training, or you pick specific columns and slice by those columns and run the metrics against those columns. Super powerful. And again, this might be really small to read right now, but like it generates statistics, and those statistics can be visualized within your components when you execute them, for example, with Kubeflow Pipelines. So we can drill into those components and then see the statistics afterwards. And the wonderful thing is also those statistics are preserved. So even if the model has shipped, we can always go back to our Kubeflow Pipelines components, and then investigate maybe in 2 months, how did the training actually look like? So if a customer comes in and says like, hey, this model is not performing as expected, we can see, did we miss something? We have all the metadata available here. We can also compare the different metrics, et cetera, et cetera. So that's all preserved. And then the last step in our short pipeline here is the model deployment. And the model deployment works hand in hand with TensorFlow serving. You actually don't host it outside or coming out of the pipeline. You basically push the model into a location where a model server like TensorFlow serving or like BentoML or an Onyx runtime setup could pick it up. So you can push those components. You can push those models to an S3 bucket or to a GCP bucket, and TensorFlow serving could pick it up. But also this pusher component can create like model serving endpoints in GCP, or what we have done internally, we have created components to create SageMaker endpoints if you're in the AWS environment. So this gives you a lot of flexibility of how you want to deploy your machine learning endpoints. But the wonderful thing is everything up to this point has to work out. It has to pass the data validation, it has to pass the training, it has to pass the model analysis. And the model analysis, and I forgot to mention this earlier, also compares against previous runs. So we can set the criteria that a model has to be better by X% than our previous models we have pushed out. And then once we define our pipelines, nothing has been executed so far. We can orchestrate them with the frameworks or with the libraries I put up here on this slide. So if you want a quick and easy orchestrated way of using your pipelines, you can use Apache Beam. It doesn't have a front end, but it makes sure that those components are orchestrated. If you already have ETL systems in your company or in your project and you use Airflow, you can easily orchestrate your pipelines with Apache Airflow. And then if you have Kubeflow running or Kubernetes running, it's very straightforward to set up Kubeflow, and you can orchestrate your pipelines with Kubeflow Pipelines. And that is a system which is specifically designed for managing machine learning pipelines, and you get all the wonderful benefits out of that. So there's one last step you need to do. You need to basically define which components go into your pipeline. You then define the configuration for your pipeline. So you say, where's your metadata store? Like, where do you store the information from each component, and so that the next component can adjust it. You can set configurations of like how many GPUs do you want to use, how many gigabytes of memory do you want to claim in your cluster if you run it in Kubeflow, etc. And then you run your pipeline. And so what I want to highlight here is if you run your pipeline on Airflow or Apache Beam, it will immediately execute. If you run it with the Kubeflow DAG runner, it will basically convert whatever you configured in Python and convert it into an Argo configuration file, which you then can use either straight with Argo or with Kubeflow Pipelines, as Carl will demonstrate in the next talk. One thing I want to stress here is metadata is everything. I see a lot of talks about machine learning pipelines, and there's not a single word mentioned about metadata, but no component could connect to each other if we wouldn't have the metadata. So TFX provides you a metadata store. It'll take care of the communication between the components. You don't have to set which are the inputs, which are the outputs. That's what the components provide you. Even in the Kubeflow DSL, you sometimes have to stitch those components together. So if you want to simplify your life, the TFX DSL provides you all those pre-made components. If you want to configure your own custom components, TensorFlow Extended is highly flexible, so you can write your components from scratch, or you can inherit existing components, manipulate some executors. So there's a lot of flexibility for you in that system. Here's a quick example of how we would run this in Kubeflow Pipelines. This is an example from our book where we have a public data set of customer complaints, and we want to figure out which customer will complain or not. So it's basically in Kubeflow Pipelines, we converted our Python setup into an Argo run, Argo configuration. We loaded that into Kubeflow Pipelines, and then we can set up, this is a menu where you can set up weekly runs or daily runs, how often you want to trigger that. You can also trigger that through S3 buckets. There's a lot of ways you can trigger your model updates. And this is one thing I want to highlight here, is the lineage. That's the model lineage, which comes out of the metadata store. So once we have trained a machine learning model, and let's say we ship this model, we can always go back to the metadata store to say, okay, we shipped this model at this date. Let's retrace it. What was the input? Which model did we use? Which hyperparameters? Who signed off? We use like components where humans sign off on model deployments, and we can check which data scientist did the evaluation, what were the criteria, et cetera, et cetera. So this is a wonderful thing where we can say, this is also preserved, so we can always go back. That's our record of what led to that model. All right, I'm getting short here on time, so we quickly want to just summarize the reasons for TFX pipelines. As I said, the metadata store is there. It helps us to make our machine learning pipelines reproducible and also very consistent. We can automate the model updates. We get an audit trail, as I just showed you in the previous slide. There are ways where you can bring the human into the loop You can have a little, we have a little component in our setup where somebody in the Slack channel gets connected or gets contacted if a model reached a certain state and the pipeline evaluated the model and said like, hey, this looks great. Can a data scientist look over the results and sign off? And then we approve that or reject it via Slack. We can also automatically convert models to TensorFlow Lite and TensorFlow JS. I think this is with TensorFlow Lite becoming more and more powerful. This is extremely wonderful. We can train 2 models in parallel. One model goes to a machine learning server, and the other model is being shipped to the mobile team. We can tune as part of the pipeline, and then the best run, the hyperparameters of the best run will be used for a final training setup. We can do pipeline branching. So sometimes you want to have a canary model, and sometimes you want to have a test model with maybe slightly different hyperparameters. We can train them in parallel. And we have finally a way to do continuous model deployments. If you're interested in all the details, I rushed through a lot of details here. I highly recommend that publication. This is out this week, so it's brand new and everything is on up to date with the latest TensorFlow versions, TFX versions, and Kubeflow Pipeline versions. Yeah, with that, again, if you're interested in all the details of the example I showed you, check out the TensorFlow blog, where we explained in 2 parts the details of how everything works inside of with Bird. And with that, thank you very much for taking the time. And yeah, if there's a couple minutes left, I'm happy to take some questions.
Awesome. Thank you, Hannes. I don't see a lot of questions, but people mentioned something about data drift. Do you want to talk a little bit more about that? Or maybe a favorite instance of data drift that you have seen?
Sorry, the favorite what?
Instance of data drift happening in model or training instances that you can talk about?
Yeah, so it's often the case when you train a machine learning model and you put it out into the wild, people react to that model. And they learn how to tweak that model to their benefit, and that usually becomes visible in the data drift. So all of a sudden, certain labels don't show up anymore or show up dominantly, and then your entire model gets biased in a certain direction. And that's the wonderful thing with the TensorFlow data validation tool, where we can generate those statistics and compare them with every data ingestion. So I highly recommend that TensorFlow library.
Awesome, fantastic. Thank you so much, Hannes. Thank you so much for the talk. Looking forward to the book, actually.
Yeah, thanks for having me. Yeah, it's quite a long journey. I'm looking forward to have the print copy for myself. So far, I've only seen digital versions. So
awesome.
Yeah, very excited about it.
Awesome. Thank you.
Thank you.
We will have next speaker joining in soon. Thank you, Hannes.
Thank you.